think we can start.
Okay. Okay, so good morning, everyone, or good afternoon, everyone, actually, for those who are in Algeria. So welcome to our, to our weekly seminar series. And today we are thrilled to have our guest speaker, Dr. Malek Mouhoub from Canada. So Dr. Malek Mouhoub is a professor at the Sask Power Research Chair in Artificial Intelligence at the University of Regina, Canada. He led the computer science department from 2016 through 2019. His research interests include constraint solving, spatial and temporal reasoning, preference reasoning, constraint and preference learning, vehicle routing, efficient grid-wide energy consumption, and precision farming and geographic information systems. Dr. Mouhoub research is supported by the National Science and Engineering Research Council in Canada, the Canadian Foundation for Innovation, and the Mathematics of Information Technology and Complex Systems federal grants, in addition to several other funds and awards. Further to that, Dr. Mouhoub is involved in scientific and administrative activities and roles. He served as the treasurer and the member of the executive of the Canadian AI Association, which is the oldest national AI association in the world and the official arm of the Association of the Advancement of AI in Canada. He chaired or co-chaired multiple international scientific events that include the Canadian Conference on AI, the International Conference on Industrial Engineering and Other Applications of Applied AI Systems, and the International Conference on Computational Intelligence and its applications. So as you can see, this is a very impressive resume and expertise. Dr. Mouhoub, we are really thrilled to have you with us today. And yeah, we are all ears and the stage is yours.
Thank you very much. Assalamu alaikum. Thank you, Malika, for the introduction and for moderating this presentation. I also take this opportunity to thank Faiz and the Algerian Scholars and Competence Abroad for organizing this productive webinar series. So the focus of this presentation is on solving combinatorial problems. And these include decision problems where we have a set of constraints to meet, as well as optimization problems where we have requirements to meet, as well as objectives, including user preferences to optimize. During this presentation, I will use the known constraint satisfaction problem framework in order to illustrate the different models and solving techniques. Now, let me start by an overview of what we mean by a constraint combinatorial problem and like the different components of that problems and the related challenges. So assume that we have a combinatorial application, like a problem and constraints and objectives. And assume we have two objectives in our problem, objective 1 and objective 2. Now let's assume that we can plot all the possible scenarios of this application on a two-dimensional space where each point will consist on the value of objective 1 and objective 2 for a given scenario. Now, let's assume that we have a set of constraints, which is the case in almost all combinatorial applications. Then, once we add these constraints, we will restrict the set of possibility to the feasible ones, those that are within the circle that I am presenting in the slide. Now, in addition to feasibility, assume that we have to minimize one of the objectives, assume it is a cost, and we want to, at the same time, maximize the other objective. Basically, we have a conflicting objective, one to minimize, one to maximize. So in this regard, among the feasible solutions, we will be looking for those that optimize both objectives. And usually we will end up with what we call a Pareto front, which is set of trade-offs that optimizes both objectives. Now, the challenge is once we solve the problem and we get this Pareto front, we will provide it to the decision maker. And in general, it will be hard for the decision maker to pick among a set of Pareto optimal solutions or trade-offs if this set is very large. So in this regard, we will add an extra step where we have to elicit more preferences from the decision maker in order to reduce the size of the Pareto front to a manageable one, so that it will be easy for the decision maker to make the appropriate decision. So now, combinatorial applications, once we have when we have constraint and objectives, are also called multi-objective optimization. So usually when we have two objectives, like the case in this example, we talk about bi-objectives. If we have three objectives, we talk about multi-objective optimization. But if we have more than three, nowadays we use the word many-objective optimization. And multi-objective optimization problems exist pretty much everywhere in the real world. So we as workers, we implicitly deal with one form of multi-objective optimization where we have a dilemma between working less and getting more money. So basically, these two are conflicting objectives, and we try to find a good trade-off for that. And students, too, implicitly, they are dealing with a multi-objective optimization where they have to look for a trade-off or compromise between working less and getting high grades. And of course, we have constraints in each case, like students, while trying to work less, getting more grades, they should meet the academic standards and the integrity. Another good example I want to show regarding multi-objective optimization, during the COVID pandemic, we experienced the dilemma, especially government officials. They have to deal with maintaining the healthy economy and healthy people. Because as you know, so they are between opening the economy, but this will have a negative impact on the health of people because it will spread the disease. So finding a good trade-off, this is what politicians and officials in different countries were looking for. Now, let me go over just a couple of projects that I was involved on, and they relate all to multi-objective optimization. The first one is a project that I conducted with the local company in Regina. And the aim here is to develop a tool that looks like Google Maps, but it's meant for transporting merchandise and goods from two locations in North America. And unlike Google Map, which is used by the casual user and where the objective is usually distance or time, so here we have a set of objectives to optimize, including distance, time, cost, fuel consumption, gas emissions. And while optimizing these objectives, of course, we have to meet a set of constraints, including road availability, driver profile, including experience, and vehicle information. For instance, since we are dealing with trucks, depending on the clearance of the truck, like dimension, the truck will not be allowed to go through some tunnels or under some bridges. So as you can see here, with all these constraints and objectives, we have to come up with an optimal path. And this is one example that becomes even more challenging since we are dealing in a dynamic environment, as I will explain later. The next example, second here, yeah, it's, sorry, second. So this example is relates a little bit to the previous one, but the goal here is to find the best tools for a set of technicians to take in order to deliver services to customers in my city, Regina. And these technicians, of course, they each start from a different location, and they have to go through a set of houses. So again, here we have, this is a multi-objective optimization where we have to optimize like distance, time, fuel cost, gas emission. The constraints are a little different. So in addition to road availability, we also have to deal with the capacity in terms of number of hours assigned to each technician. The next example is related to the healthcare personnel scheduling, which is a very challenging task, especially with the pandemic. And here we have to come up with a schedule that meets a set of constraints, including hospital policies, demand, the regulations, and optimizes costs, risks, patient well-being. And in addition to that, we have to optimize nurses' preferences. Basically, we try to make all nurses or healthcare personnel equally happy or equally unhappy. The last application that I'm showing, this is a recent project that I'm involved on, is to use a set of aerial and ground robots in order to conduct precision farming mission. In particular, it is about eliminating weeds from field crops. And in this regard, we have two specific missions. The first one is called weed mapping, where we send a set of robots to go and take pictures and build a map where we identify locations of weeds. And of course, this is again an objective optimization. You have to optimize flight time, energy consumption, field coverage, and you have to meet some constraints. So the next one consists in, after we build the map, we send another set of robots to go and eliminate weeds using laser, pesticides, or mechanical removal. And again here, this is an optimization problem where we have to optimize time, pesticide use, energy consumption, safety, field coverage, and weed suppression. So as we can imagine here, for each of these applications, we have a set of challenges to deal with. The first challenge is that we are basically searching for one feasible or set of Pareto optimal solution in case of optimization in a search space of exponential size. So the algorithm or the technique that we will design have to face this challenge. And so we have to think in terms of overcoming this challenge in practice. Like in theory, we know that this requires an exponential time algorithm, but how can we improve this running time in practice? And this is the first topic that I will cover in this presentation. The second one is, well, even with using sophisticated search algorithms, sometimes we cannot provide a solution within a given deadline, especially when it comes to real-time applications. So in this case, we have to look for alternate methods that trade running time for the quality of the solution. Like basically, instead of returning an optimal solution, we are okay with one that is near to optimal as long as we meet the time deadline. And that's the second part that I will cover in this presentation using meta-heuristics algorithms. The third challenge comes with the fact that most of these applications operate in a dynamic environment where things changes and we are facing unpredictable events. Like, for example, if we talk about nurse scheduling, what happens is one or a couple of nurses is sick. So how can we reschedule in real time without disturbing the schedules of the other nurses as much as possible? The other challenge is also on top of objectives, how can we deal with user preferences? How can we capture them? And how can we make, like nurses, for example, all equally happy? And in addition, often we don't have all the information of the combinatorial problem. So some information are incomplete, others comes with a degree of uncertainty. So how can we model and capture this uncertainty in order to solve the problem? And this is the third topic that we will cover. And finally, when it comes to solving a combinatorial application, first you need to model it in terms of variable, constraints, and objectives. And in the real life, so when you go and talk to an expert, for example, if we take again the nurse schedule problem, if I talk to the expert who used to schedule the nurses and the healthcare personnel, it is hard for the expert to come up with a formal definition in terms of variable, constraint, and objectives. However, we might elicit interactively with these experts by showing them examples of schedules, and they will just reply, well, this is a correct one, this is not a correct one, this is an optimal one, this is not an optimal one. And we use this method in order to elicit the different constraints and consequently model this problem automatically. And this basically constitutes the outline of this presentation, and I will move forward with the first topic, which is the systematic search. So to illustrate the systematic search, I will use the constant satisfaction problem paradigm. And I will take two simple examples. The one on the left is the n-queen problem, which consists in placing n queens on n by n chessboard such that no two queens threaten each other. Basically, we want to put queens such that queens are not on the same row, same column, or same diagonal. And the example on the right is the map or the graph coloring problem, where we have to color a set of regions such that no two adjacent regions will have the same color. So using this constant satisfaction problem or CSP paradigm, the problem is defined in terms of variables, their domains of values, and constraints. So if we take the example of the n queen, more precisely 4 queen in the slide. So we first need to identify what are the variables. So we can, to simplify the problem, we can decide that each queen will be on a separate column, which is one of the requirements. And once doing that, we will know now that, well, there are 4 possibilities now for queen 1, which is each of the 4 rows, and 4 possibilities for queen 2, 4 possibilities for queen 3, and 4 possibilities for queen 4, and this is how I define my domain. Then the constraints that I have to represent are the fact that queens should not be on the same row nor on the same diagonal. And the example on the right is easier because variables obviously here correspond to different regions, and the domain is the color that I have in hand to color the different regions. Constraint is basically any 2 adjacent regions should have different colors. Now, when it comes to constraints, we can define them intentionally, like symbolically, or we can define them in extension, as I will show in the next slide. And here, basically, what we show is once we have the representation by CSP, we can have a graph visualization, especially when the CSP have binary constraints. And in our graph, nodes represent variables, and edges represent the different constraints. One advantage of using graphs is if the graph fulfills some properties, like if it doesn't have cycles, then we will know that this related problem can be solved in polynomial time, so we don't need a sophisticated search algorithm. And a typical case here is if we take the Canadian map, when we only focus on the Canadian provinces, if we represent them by the graph, this graph is actually a tree. There is no cycles, and we know that it's this problem we can easily solve it. The goal, of course, when you formalize a problem using a CSP is to search for a solution that satisfies all the constraints. So in the example that you can see on the slide here, there is conflict in both problems. And here is a case where you have a complete solution for each. Like there is absolutely no constant violation for each of these 2 problems. Now, the challenge, as I mentioned before, is when we are dealing with a CSP with n variables and the domain size is d, then we have an exponential set of possibilities, d to the power of n. And this is, of course, challenging, especially when n is very large. We are
Oh, Dr. Mouhoub, can you unmute yourself? For some reason, you are muted. Sorry for that.
So hopefully this was just lately.
Yeah, just 1 second, I guess. Yeah, so we
Oh,
will.
that's
Yeah.
odd. Yeah, anyway. Yeah, please let me know in case I'm muted again. Thank you. Yeah, so as I mentioned, so we use to deal with this exponential cost, we use with systematic search, and we add other sophisticated techniques, including constraint propagation, variable and value ordering, as we will see in the following slides. And the other thing that we can do, as I mentioned before, if we cannot return a solution within a certain deadline, we can rely on meta heuristics that trade the running time for the quality of the solution. And the idea of the meta heuristic basically is very simple, because if, for instance, I give you the n queen problem, 8 by 8 queens, and I ask you to find me a solution, even if you are expert and you have experience with solving n queen, it will take you some time before you come up with a solution. However, if I give you a scenario, like I did the assignments myself, and I tell you, is this a solution? It will be easier for you to go through the different constraints and identify conflicts in any, or to tell me, well, this is a solution, I don't see any conflict. So basically, it's easier to check whether configuration is solution, but it's harder to find one. And by taking advantage of this property, we can design an algorithm that can start with a random configuration, check whether it is a solution, and this can be done in n squared if our CSP has only binary constraints. And if not, we will keep iterating by solving constraints in an incremental way until hopefully we find a solution, or at least near to optimal one. Anyway, so let's move on now first with the systematic search techniques, and the meta heuristic, we will see them in the next talk. So basically, the idea here is you just start with an ordering of the different variables, and you try to assign provide an assignment for the first queen, then try to find one for the second queen that does not conflict with the first one, and then you move to queen 3 if no violation. If there is violation, you keep looking for a value in the current queen until the constraint is solved. If there is not such value, you backtrack until you find the solution. And the challenge with this algorithm, although it is an acceptable one, is that first, it fails several times for the same reason. And second is that so often when we assign a set of values to variables, like we have n variables here to assign, assume when I reach the variable n, after I find the correct assignment for the first n-1 variables, once I reach variable n, I tried all the possible values and none work with the previously assigned variables. So if we use the standard backtracking, basically we will backtrack to the previously assigned variable, which is n-1. But the problem here is, in this example, constraints are defined in red. When you go to n-1, you are not going to solve the problem because there is no constraint between n and n-1. So basically, you are not solving the problem here. And you should rather backtrack to I from n, because n shares a constant with I, or to all the way to the top to a variable 1. And this is what the improvement of backtracking does. So when there is a conflict, we don't backtrack to the previously assigned variable, but to the one with which there is a conflict. Now, while doing so, if you back jump from n to I, well, you go to the source of conflict, but any variable in between, you will have to redo, which might take even a longer time. So, and the remedy to that is to use dynamic backtracking. So basically, before you back jump, you move any variable that has been satisfied before the variable that you are jumping to. So in addition to these techniques, we can use what we call constraint propagation. And constraint propagation basically follows the idea of a look-ahead strategy. So for instance, you as a human, once you place, for example, the first queen on the first position, you will know that you cannot put any queen on the first row nor on the main diagonal. So you will eliminate these values from the domain of the non-assigned variables. So you basically you reduce the search space before even you move to the next variable. And we can even do better than that. So if I start, for example, with the first assignment, once I put the queen, I know that I cannot put any queen on the first row, or main diagonal. But in addition to that, if we look to queen 2, I have only two positions left, 3 and 4. But I know if I put queen 2 in position 3, then this will not work because it will conflict with the remaining position for queen 3. So this one will be eliminated. And I am left with only one possibility for queen 2. So queen 2 at position 4 works with queen 3 at position 2, but queen 3 at position 2 does not work with any possibilities in queen 4. So I will have to remove it. And once I remove the second position for 3, then I will remove the last and remaining possibility for queen 2. And I know from here that, well, the first decision that I made is not a good one. So I backtrack and then I go for the other possibility and I can get the solution in 2 steps. 2 steps, but of course, each step comes with lots of effort. Now, whether this effort, this extra effort pays off or not, so this depends on experiments. Like there are a lot of work that has been investigated comparing this method, if we look at with the previous one, in terms of which one really at the end find you the solution sooner. Now, the last part that I want to add in regard to systematic search techniques is we need to also decide on which value to choose first. So we cannot just go through an arbitrary choice. And usually we try, if we have additional information on the problem, we try to use the least constraining value. In terms of variables, we do the opposite. We choose first the most constrained variable because we want to, if there are a lot of issues, we want to know them sooner. Now, defining the most constrained can be implemented in different ways. And first, we can have static ordering versus variable ordering. Static ordering, basically, before you start the problem, you decide on an order and you stick with it until you find the solution. Dynamic ordering is an ordering of variable that changes while you are looking for the solution. And in addition, defining most constrained can be in regard to the domain size, like small domain means more constrained, or it can be to the constraint, the number of constraints that variable is connected to, or it can be a ratio of both. And in addition, we can use like machine learning techniques to learn those constraints that are hard to solve, and then we can order variables accordingly. So this pretty much concludes with the first section in regard to systematic search. So in heuristic search, as I mentioned, it is about trading running time for the quality of the solution. And regardless of the meta-heuristic that you want to use, you have to be between 2 main strategies, which are exploitation versus exploration. Exploitation means you intensify the search in order to converge through a feasible or an optimal solution. But while doing so, you might have early conversion or stuck in what we call a local optimum. So, and this is why you need to combine it with some randomness. Randomness will give you more diversity and allow you to explore more promising areas. And exploitation like translate to convergence versus diversity. And I have can use the same example I showed you before and explain like what we mean by a poor diversity. So a poor diversity means when you get some optimal solutions in your Pareto front, but you miss some others that might be very relevant. On the other hand, a poor convergence means when you have diversity, but none of the solutions that you get is an optimal one. So you need to balance both. in order to have solutions that are at the same time optimal and as diverse as possible. And in terms of meta-heuristics, so there is a large class of meta-heuristics. This topic is actually very, very popular. I mean, almost every week I see a new paper on a new meta-heuristics. But guess what? In many cases, people are inventing names rather than algorithms. So some of the algorithms actually they look and they are similar to each other, and basically what the researchers do just came up with a new name of an animal or a property or anything else. But if we want to classify them, so we have two main categories. The first category is called the trajectory-based meta-heuristics, which basically consists on starting with one single configuration and improve it until you get a solution, versus what we call a population-based meta-heuristics, where instead of starting with one single configuration, we start with a set of candidate solutions and then apply operators until we find a solution. And the meta-heuristic, especially the population-based ones, are inspired by nature. So they can be bio-inspired, like swarm intelligence, evolutionary algorithms and organism structure. They can also inspired by physical or chemical phenomena. Now, in terms of combinatorial optimization, the first step when using a meta-heuristic is to define a discrete version for it, because many of the meta-heuristics have been designed for continuous problems. And the key points to focus on when finding a discrete version for a meta-heuristic algorithm is to first define what we mean by a candidate solution on an individual and the population. So the traditional model that we adopt is basically we use a vector where each entry corresponds to a variable value. In addition, we have to redefine the exploitation operators so that they work in discrete spaces. And these operators, they include distance between like candidate solutions, movement, neighborhood, and others. So for instance, the distance, which is a very important parameter in many nature-inspired techniques, like the one that I will show a bit later on, is called the Hamming distance, which basically, if you have two configurations, the Hamming distance corresponds to the value that are different in both candidate solutions. So this Hamming distance has to be used in discrete spaces instead of for example, the Euclidean distance, which is used in the continuous space. So now, if I take one trajectory-based method, which is called local search, and more precisely, in our example, we have a mean conflict based method. So I take again the 4-queen problem. So basically, I take a 4 queen, just randomly put them on the chessboard, and then identify the conflicts. This can be done in n². And once I do that, I pick a variable that is involved in most conflicts. So I can pick either the queen 2 or queen 3, because each of them is a variable is involved in 3 conflicts. And then I would find the value for that queen that minimizes the conflict. So for example, if I pick queen 2, so if I give position 1 to queen 2, then I will reduce its conflicts from 3 to 0. And then I will do the same. So I pick the variable that is involved in most conflicts. In my case, it's queen 3. And then I find the best value for it, which is value 4, and I solve the problem. Of course, it's not always the case, because sometimes when you are trying to satisfy the constraint and doing the repairs, you might be stuck in a local optimum. For example, you might end up with one conflict and you can no longer improve, in which case you have to add some randomness and exploration. So now let me show you an example of a population-based algorithm. So we take the map coloring or graph coloring problem here. So I have 4 regions. For each one, I have a set of colors, not the same colors. And the first step, if I use this evolutionary technique that's called genetic algorithm, so I need to start with a set of candidate solution. For each candidate solution, I have a complete assignment of colors to each variable. And after that, what I will do, I compute the fitness function, which corresponds to the number of violated constraints that I need to minimize. And I apply two operators, mutation and crossover. So when applying these operators, my first goal is to conduct exploitation, like try to improve, as we will see in this example. Every time we apply, we get a better solution. But we also use mutation for exploration. So sometimes we, in order to add randomness, and depending on the problem, we can have sophisticated mutation operators. Now, of course, on top of that, of this population-based algorithm, we can use the parallel versions. So now, in the past, like 20 years ago, it was very hard to get access to a true parallel powerful machine. But these days, I mean, if you take just a graphic card, you can use an environment in order to use it for parallel processing. And this is what I did with one of my graduate students. So basically, we take the genetic algorithms, and then we design a complex architecture of a set of islands. And each island here contains a group of genetic algorithms that are running in parallel. And what we do, basically, we first use one component that is called estimator that gives us a good, some good with candidate solution. We pass them to the parallel architecture. And then this parallel island that you see included, they pass messages between each other. So for each island, they look for a solution, but whatever they discover, they will pass it to the other islands, and we get the solution sooner. By doing so, we were able to like push the boundary and solve this graph oral problem with amazing results. So the last population-based algorithm that I want to show is called the particle swarm optimization, which is one of the most popular. Just to give you an idea on the difference between the nature-inspired techniques. So in a particle swarm optimization, we have what we call a set of particles. And each of these particles corresponding to a candidate solution moves randomly with a certain parameter W, as well as moving toward its best location. Because for each particle, we store its best value. So, and to balance this exploration exploitation, as I said, this particle moves a little bit randomly with a certain parameter W, and then it moves a little bit towards its local best or personal influence using two parameters C1, R1. And finally, it moves to the global best, which is the value of the best particle, using, again, other parameters. And with the proper tuning of these parameters, we will allow a good balance between exploitation and exploration, and which will allow us to have particle improving until hopefully we will get the feasible optimal solution. Let me see, I'm doing in terms of time, so I have to hurry up a little bit. So the next part that I will cover here briefly, it consists in dealing with the CSPs that operate in a dynamic environment. So what happens in case where after I get a solution, like feasible solution, I have to add or remove some constraints. Well, if you remove constraint, your solution is still feasible. But maybe in terms of optimization, maybe there is a better one that was not available because of the constraint that I just removed. But when you add in constraints, there are chances that your solution is no longer feasible, and you need to look for a way to find the new solution such that the new solution is not that different from the initial one. For example, if we talk nurse scheduling, let's assume that a couple of nurses are sick and we have to reschedule. So the new schedule should meet all the requirements as before, optimizes all the objectives as before, but on top of that, it should not be that different from the initial schedule, because we don't want to disrupt the schedule for all the other nurses. And there are, of course, a large number of systematic and approximation techniques for dealing with dynamic problems. I will focus on one that I have introduced with my graduate students, and it's based on heuristics. And basically, it follows the idea that when you use a meta-heuristics, especially population-based method, at the last stage, once you get the optimal or near optimal solution, you save context of the last iteration or the other candidate solution, because these are promising solutions, even if they are not optimal. We keep them there in case the problem changes. We will start with those candidate solutions that I got at the last stage to check whether one of them can be the new best. If not, we gradually move to the nearby solution. If we don't find, then we gradually do a little more exploration until we find a new solution. And this is basically one good way of dealing with dynamic problems. So as for adding preferences, so I showed you in the example before that we rely on preferences at the end. Okay, so after we get the set of Pareto optimal solution, so we elicit preferences from the user, and then this help us to reduce the size of the search space. This is called a posteriori decision making. So basically, you solve the problem, and then you add preferences on top in order to reduce the Pareto size. There is a different strategy, which consists in using the preferences beforehand, before even you solve the problem. So basically, when you add the preferences initially, the goal here is from the start, you add a property or a relation that allows you to rank the different objectives or quantify their relative importance. And by doing so, basically at the end, once you get the solution, you have the elements already sorted, and you don't even need to reduce the Pareto set, because you have additional order on these Pareto optimal solutions. Now, in terms of preferences, they can be quantitative or qualitative. So quantitative is numeric, like if you go to any recommender system, so usually they will ask you to rate your satisfaction from 1 to 4 or 1 to 10. This is quantitative. In terms of qualitative, you use an ordinal ordering. So instead of providing number, you can just say, I like this item better than the other one. And the quantitative preferences, they can be modeled with what we call a soft CSP, which is an extension to a CSP. So basically, the classical CSP, the fitness or the objective function is the number of variable constraints that we want to minimize. Of course, hopefully we want to get 0 constant violation. But we can extend the CSP to handle preferences by defining a utility function on the as the natural number. If we are dealing with the probabilities, like if we are dealing with the constant that comes with a degree of certainty, so we can either use the probabilistic or possibilistic reasoning. In the possibilistic reasoning, basically we are more talking about the degree of truth, while in probabilistic reasoning we are talking more about the probability for a given event to be true or not. As for the qualitative preferences, so usually researchers rely on graphical models for representing conditional qualitative preferences. And I can explain it with the following example. Let's assume that I have 3 attributes here, x1, x2, x3. x1 and x2 attributes, their value are ranked unconditionally. But for attribute x3, the preference of the values depends on the value that I assign for x2. So say, for example, if I tell you what's color of a car you will like, you tell me what it depends on the type of car. So if it is Ferrari, for instance, you rather like a color red because it goes well with the brand, and so on. So these qualitative preferences are hard to implement or to represent quantitatively, but using a qualitative model like this, we can represent them. And this model is meant to be a compact one because it actually represents an exponential set of outcomes that are connected to each other, from the worst to the best. So a direction here from one outcome to the other means you are moving from one to a better one. And of course, once we follow this property, we can identify the worst outcome versus the best one. Now, if we add constraints on top of these preferences, we will cancel some of these outcomes. And by canceling, if one of the outcomes that you cancel is the optimal one, because when we're dealing with just preferences without constraint, we have one optimal outcome, which is x1, x2, x3 in our example. So if we cancel the optimal outcome, for the next best, we might have more than one. So we might end up with, again, a Pareto set of optimal solutions. And this is, of course, a very challenging problem to solve. Now, let me move to the last part in regard to constant and preference learning. Although there is an opportunity for using machine learning to learn from historical data, like with one of my students, what we do for the case of the nurse scheduling problem, we take the past history of all the schedule of nurses in the past, like 5 years. And then we just run a machine learning model to learn from the past data and predict a new schedule.
Dr. Mouhoub,
yes?
Sorry to interrupt. So we have 5 minutes left for the talk, so we can leave time for questions. There are more than 10 questions in the chat. So if you can wrap up the talk in 5 minutes, that would be great.
Okay, sure. This is all what I need. Thank you.
Okay, perfect.
Yeah. So, and here, as I said, we use a different, I want to show a different approach. And this is about exact learning. So basically, you interact with the user. When it comes to preferences, you just give 2 outcomes and you ask the user which one is better. If it is a constraint, you just give a scenario, it is scenario consistent. And of course, the challenge here is to reduce the number of queries, again, using content propagation and subordering heuristics. So finally, so I will list here some concluding remarks. So my first remark is, and this is some mistake that many students do. Usually they rush into meta-heuristics, thinking that all meta-heuristics are faster, so I will use meta-heuristics because a systematic search method, it takes an exponential running time. You should always give a chance to a systematic search method and try to do your best to come up with an optimized algorithm before you decide to go with the nature-inspired technique. And second remark is, when you are using a meta-heuristic, regardless of the algorithm, and as I said, there are many of them, but they all follow very important notion, which is balancing exploration exploitation. So you should come up with a good tuning for your parameters, and now there are like systems and tools that allow you to tune your parameter to their best, like ERVA, REVAC, FRACE, and so on. And this helps you to tune the parameter of your meta-heuristic, because this is key when using meta-heuristic. The third one is, rather than seeing exact versus meta-heuristic as methods that compete with each other, we can use advantage of one and the other to design a new hybrid techniques. And there are some work, of course, in this regard. And the last component is, of course, machine learning now is one of the most popular topic, and so is the combinatorial optimization, multi-objective optimization. So we can rely on machine learning to learn constraints, learn preferences, even learn the solving strategies. Like I have worked with students where the goal is you have a set of meta-heuristics and we choose the right one for the right problem. After we train a large set of problem instances, so we can automatically generate the appropriate meta-heuristic algorithm depending on the features of the problem. And on the other hand, we can use combinatorial optimization for improving machine learning, for parameter tuning in machine learning, because this is a special case of combinatorial optimization, and also for dimensionality reduction and feature selection. So how to choose the best subset of features that optimizes accuracy or other clustering or classification methods. And this concludes my remarks. Thank you for your attention.
Great, thank you so much. This was amazing. I got more than 10 questions, very highly interesting question in the chat, but I will open the floor first to anyone who wants to ask his or her question in person. So if I don't hear from you in the next 2 seconds, I assume that no one wants to ask an in-person question. So let's move on to the chat questions then. And I will start by the end. Are there specific architectures to follow for combining machine learning models and classical combinatorial optimizations methods such as meta heuristics?
I mean, I don't know what is meant by architecture. So it depends on the problem that you are tackling. So is it initially a machine learning problem, or is it a combinatorial optimization problem? So for instance, if, as I mentioned before, is it about using machine learning for the sake of multi-objective optimization, or is it using multi-objective optimization to improve on machine learning techniques? And for each case, we might have a different model to apply. Like I just briefly.
Hello.
Yes.
So I'm the one who asked the question.
Yes,
so
please,
my name
go
is
ahead.
Iman Abdelrahim. So if you just, it's more actually for the sake of including machine learning models into meta-heuristics for solving combinatorial problems.
Yes. So basically, you
So
want to take.
what
Yes.
is like, yeah. So like, are there any best ways or how to include this machine learning models into the meta heuristics, or like at which level we include them?
Yes. So the first level is for the modeling part. So instead of modeling your problem manually, like identify the variable, because before you use your meta-heuristic, you need to come with a good model for your problem. You need to identify the decision variables, and you need to identify the constraints and the objectives. So first step is use machine learning in order to model your problem. So here there are no architecture used, like no specific architecture per se to use. You can use, there are two main ways. One way is to use machine learning models like deep learning, for instance, to learn from historical data. So if we talk about like scheduling or other problem, we assume you have a large set of problem instances that you have already labeled as optimal or not optimal, or satisfiable or not satisfiable. And then you can, after that, get a new model using a machine learning technique. But there is a problem here when it comes to modeling. And this is something I want to highlight. And this is what we faced when we dealt with nurse scheduling in hospitals. And this is goes to maybe Malek and Faiz, they might have some idea also on that. When we learn from historical data, there is always a bias. Like in Montreal, for example, they have one of the largest hospitals in North America. And we try to extract preferences from different nurses. But guess what? When we extract preferences, they come with a degree of subjectivity. Because after a deep research, we want that the preferences that we have obtained do not correspond to the satisfaction of nurses. Because some nurses have strong personality. They always fight for the best time. But others are shy. And we cannot see that from this schedule. So this is one problem when you are doing machine learning in the case of modeling. So dealing with the bias. Now, in addition to using machine learning for modeling, in terms of meta-heuristics, you can use machine learning, for instance, to find a good balance between exploration and exploitation. That's one other possibility. The third one, which is something that I have used with my students, as you know, meta-heuristics, there is no single algorithm that solves all the combinatorial problems. Each meta-heuristics or its meta-heuristic algorithm works best for some problems, but not others. So with my students, what we did, we use what you call a portfolio optimization, where we take the best maybe 20, 30 meta-heuristics, and then take 1 million problem instances. And what we do, we convert them into images, And then we take the 20 problems here and we run 20 algorithms, and we run them on all these problems. And we compute how much time it takes for each algorithm to solve a particular problem, and then what's the quality of the solution. And after we did all that, so we are able to learn from this experimentation on 1 million problems, what is the best algorithm for the type problem. So that if we have a new problem, what we will do, we will look for the one that is the similar one from those that we have learned before, and then we use the appropriate algorithm. So you can use it to select the meta heuristics. So you can use to model the problem, to select the meta heuristics, and third, to, as I said, find the good balance between exploration and exploitation. But as for system, there is not nowadays. This is still a very hot topic that people are still investigating.
Thank you so much. So next
Thank
question.
you so much.
No problem. My
Next
pleasure.
question, how sensitive is the solution to changes in preferences, and how can one identify solutions that are robust across various preferences scenarios?
That's a very challenging question. I hope I have this answer this question. So depending on the problem, some problems are highly dynamic, like things change by the minute. For example, if you are looking for the best tour in a city like Paris, for example, even Algiers, so there is a lot of congestions, and what you consider as the best route at a certain time might not be so in 5 or 10 minutes. So now if you are talking about preferences, it might happen. And this is very challenging because I mean, a human being are very even complex in terms of providing their preferences. So I was a department head in my department 3 years ago. So basically what I did, before I scheduled classes to the different profs, I looked to the past schedules. And I assumed that if a prof was teaching a class, same class for 20 years, then they liked this class. And actually there were two scenarios that I was challenged with. First one is the prof said, no, I hated this class, but I was given this class first time and I was shy to fight. And the second option, prof, I like it last year, but now I am bored. I want to choose something else. So you can face this situation. Now finding the robust solution, it depends on many parameters, and it's not an easy task. First, also, you need to decide on whether you go for a probabilistic reasoning, like using probabilities, or using fuzzy logic as a model. And then you need to see how much data you have in hand to learn from. Do you have enough data in order to know how to extract representative preferences? And you need to sometimes make compromise, because if we have many preferences that change a lot, it will be a tedious task to find a robust solution. So yes, for some problems, it's not hard to find a robust solution that sustains these changes, but for others, it might be very hard. And one last thing I want to add, and this is something that I am currently exploring with my students, is we use reinforcement learning. Because reinforcement learning follows pretty much the idea of meta heuristic in terms of exploration, exploitation. So because you are moving from one state to the other through actually a balance between exploration and exploitation. And with reinforcement learning, is good in terms of reacting to events. Like the example I showed you for the set of robots that we sent to a farmland in order to detect and eliminate weeds. When it comes to working in real time, because now the new problem that the company is asking us is to have the same robot doing both missions. Same robot goes, find the weeds, and eliminate it right away in real time. So we find it very hard to use like traditional technique to solve problem. But when we added reinforcement learning, find it that it is very efficient to react to these sudden changes. So my answer is try reinforcement learning. You might get good results with these challenging dynamic changes.
Perfect. And this is a question actually related more to application of ML and machine learning and AI in medical research or in biology. Actually, I really liked the section of your talk where you were referring to backtracking. So what's the cost of backtracking in method optimization, especially when we deal with biological data and we want to make predictions about, you know, vaccine response, for instance, or disease progression? How do you think about the use of backtracking with some kind of scoring system to penalize or not maybe this in terms of outcome, final outcome?
Yes, a very good point. We tried this for a couple of years, and it was very time consuming. Like we were frustrated by I mean, we get good results. So you just need to know how to backtrack, as I said, because the standard backtracking, sometimes they don't backtrack to the right place, to the source of reason. So you need to identify where to backtrack. And for that, we need to combine it with some machine learning, as long as you have data to learn from. So again, here, we were challenged by the running time. So we now are thinking more in terms of reinforcement learning. That's one idea that we are adding on top of backtracking. But yes, these, I mean, when it comes to microbiology, things are even way harder. I mean, in my presentation, I have several slides on DNA sequencing, for example, because I work on temporal problems. Because in temporal problems, so you have if you imagine two time intervals, and so you can have a set of possible qualitative relations, like one interval is before, or it overlaps, or it's within, and so on. And we find that in DNA sequencing, they have similar relations. So we try to use them in order to identify some patterns. But still, as I said, we are challenged by the complexity because it's a huge when it comes to do that. But again, with backtracking alone, we were frustrated by the results despite everything that we added. And now we are relying on machine learning technique, and hopefully we can get better.
Perfect. Unfortunately, it's already 12:07 and we need to wrap up the call. So please, if you have more questions to ask, we will be happy to share. Dr. Mouhoub, if you are okay, we share your email with who wants to discuss further or have more questions to ask. And advise if you can post in the chat Dr. Mouhoub's email. So thank you so much for joining today. Thank you, Dr. Mouhoub, for your amazing talk. And we would love to have you again for another amazing, exciting talk in the future. And yeah, thank you and enjoy your weekend.
Okay, thank you very much, Malika, for moderating this tutorial. It will be my great pleasure to answer any questions that any researcher or student has. I would be more than happy to answer any question. And yeah, feel free to share my email address with everyone.
I can share it now for sure. Yeah. And so yeah, just one second.
Please,
you can directly, Monsieur Mouhoub, if you want.
What is that, Faiz? I couldn't hear you. What did you say?
Oh, I said I will do it for sure. Yeah.
Oh, yes. Perfect. Okay.
Yeah.
Thank you so much. And please don't hesitate to send your questions to us, to Faiz, myself, or Dr. Mouhoub, and we will be more than happy to try to answer. It was a really exciting.
Sure.
Yes, thank you very much. I see that some people are looking for more details. I mean, it is hard in 45 minutes presentation to go through the details.
Yeah.
I know, like in computer science, we say the evil is in the details.
Exactly.
But, unfortunately, we cannot use the evil here. When we have, I try to do a broad presentation. Let's explore in breadth, not in depth. But I will be happy to give any clarification.
It's quite interesting. Thank you. Thank you very much.
The email is posted, so
they can take it.
Okay.
Okay, so thank you for everyone, and like let's
see you next time.
Thank you very much. Thank you very much, everyone. Assalamu alaikum.
Bye.
Bye. Bye. Bye. Bye.
Bye.